Hello, class, and welcome to Chapter 10, Section 2 of the mole mass and mole volume relationships. This will be another kind of tricky chapter, so we're going to take our time with this. If you guys have any questions about this, please let me know. So the mole mass relationship, the molar mass of an element or compound to convert between the mass of a substance and the moles of the substance. This is what we mean by when we say the mole mass relationship. The conversion factors for these calculations are based on the relationship that a molar mass will equal 1 mole. So we have the molar mass to 1 mole and 1 mole to the molar mass, and that is what our conversion factors will be. So we have a sample problem number 10.5, converting moles to mass. Items made out of aluminum, such as aircraft parts and cookware, are resistant to corrosion because the aluminum reacts with oxygen in the air to form a coating of aluminum oxide, which is Al2O3. This tough resistance coating prevents any further corrosion. What is the mass in grams of 9.45 moles of aluminum oxide? So we list the knowns and unknowns. The mass of the compound is calculated from the known number of moles of the compound, and the desired conversion is moles to mass. So the knowns are the number of moles, which is 9.45 moles of aluminum oxide, and the unknowns will be the mass in grams of aluminum oxide. To solve for the unknown, we need to determine the molar mass of 1 mole of aluminum oxide. So aluminum oxide, there's 2 atoms, and each atom has the mass of 26.98 grams that you can get from the periodic table, plus 3 oxygen molecules, and they're each worth 16. So we're taking 2 times 27 about, plus 3 times 16 to get the molar mass of 1 mole of aluminum oxide, which is 101.96 grams per mole. Then identify the conversion factor relating moles of aluminum oxide to grams of aluminum oxide. And we just calculated that there's 101.96 grams of aluminum oxide in 1 mole of aluminum oxide. And then we'll use that relationship. 1 mole of aluminum oxide is equal to 101.96 grams of aluminum oxide. And again, we took that by taking the number of atoms and multiplying by the mass in the periodic table. So we'll multiply the given number of moles by the conversion factor. So they tell us that we have 9.45 moles of aluminum oxide, and we'll multiply by the 101.96 grams of aluminum oxide for 1 mole. The moles will cancel out, and we'll be left with the number of grams of aluminum oxide, which is 964 grams of aluminum oxide. Does the result make sense? The number of moles of aluminum oxide is approximately 10, and each has a mass of approximately 100. So the answer should be close to 1,000, and it was. So we use the answer, and then we round it to the correct number of significant figures. Let's do another sample problem. When iron is exposed to air, it corrodes to form a red-brown rust. Rust is iron 3 oxide, Fe2O3. How many moles of iron oxide are contained in 92.2 grams of pure iron oxide? So we'll do the same thing. Let's identify the knowns. The number of moles of the compound is calculated from the known mass of the compound. And again, the desired conversion is mass per moles. So the knowns are the mass they give us. We have 92.2 grams of iron oxide. And our unknowns is we want to find the number of moles of iron oxide in that mass. So solving for the unknown, we determine the molar mass of 1 mole of iron oxide first. And again, we get these mass units from the periodic table. We take our iron 2 times 55.85 grams, that's found in the periodic table, plus 3 oxygens at 16 each. So we'll get the molar mass of 1 mole of iron oxide is 159.7 grams per mole. Then solving for the unknown, we use that conversion factor. 1 mole of iron oxide is equal to 159.7 grams of iron oxide. And we need to note that the known unit grams is in the denominator and the unknown unit moles is in the numerator. Solving for the unknown will multiply the given mass by the conversion factor. So we're given 92.2 grams of iron oxide, but we'll multiply it by the conversion factor, making sure we put grams of iron oxide in the denominator so that they'll cancel out. So then we'll get the number of moles in 92.2 grams of iron oxide is 0.578 moles of iron oxide. Does the result make sense? The given mass is about 90. It's slightly larger than the mass of 1/2 moles of iron oxide, about 80. So the answer should be slightly larger than 1/2, about 0.5 moles. So that does make sense. Then we'll talk about the mole volume relationship. So the volume of 1 mole of different solids and liquid substances are not the same. The volume of 1 moles of a gas measured under the same physical conditions are much more predictable. Avogadro's hypothesis states that equal volumes of gases at the same temperature and pressure contain equal number of particles. The particles that make up different gases are not the same size. However, these particles in all gases are so far apart that a collection of relatively large particles does not require much more space than the same number of relative small particles. Whether the particles are large or small, there will be large expanses of space that exist between individual particles of gas. And I think we just are stating that again, whether the particles are large or small, large expanses of space will exist between the individual particles of gas. The volume of a gas will vary with a change in temperature or a change in pressure, and the volume of a gas is usually measured at standard temperature and pressure. That's abbreviated STP. So this would be 0 degrees Celsius and a pressure of 101.3 kilopascals or 1 atmosphere. At standard temperature and pressure, 1 mole, or 6.022 times 10 to the 23rd representative particles of any gas will occupy a volume of 22.4 liters. So that's the number of liters that 1 mole of any gas will occupy at STP, standard temperature and pressure. The quantity, 22.4 liters, is called the molar volume of a gas. And calculating the volume and moles of gas at standard temperature pressure we will do now. The molar volume is used to convert between the number of moles of a gas and the volume of the gas at STP, and the conversion factors for these calculations are based on that relationship, that there are 22.4 liters of that gas, and that's equal to 1 mole at standard temperature and pressure STP. Calculating the volume and moles of a gas at standard temperature and pressure, you can use those conversion factors then to convert a known number of moles of gas to the volume of that gas at STP. And you can convert a known volume of the gas at STP to the number of moles of that gas. So let's do sample problem 10.7. Sulfur dioxide, SO2, is a gas produced by burning coal. It is an air pollutant and one of the causes of acid rain. Determine the volume in liters of 0.6 moles of sulfur oxide gas at STP. So let's first identify the knowns. Our knowns are that since sulfur dioxide is a gas, the volume at STP can be calculated from the known number of moles. The number of moles that they give us is 0.6 moles of sulfur dioxide, and we know that 1 mole of sulfur dioxide is equal to 22.4 liters of sulfur dioxide at STP, and we're trying to find the volume of liters of sulfur dioxide. Identify the conversion factor relating the moles of sulfur dioxide to volume. And we know that 22.4 liters of sulfur dioxide is equal to 1 mole sulfur dioxide at standard temperature and pressure. So that following relationship will apply for gases only at STP. 22.4 liters is equal to 1 mole. So that's the conversion factor we will use. So we'll multiply the given mass by that conversion factor, 0.6 moles of sulfur dioxide times, and again, we want to make sure we put the moles in the denominator so they will cancel out, We'll multiply that by 22.4 to equal 13 liters of sulfur dioxide. Does this result make sense? So 1 mole of any gas at STP has a volume of 22.4. So if we're asking for 0.6 moles, it should be slightly larger than 1/2 of the mole, or 11.2. So that does make sense. The answer should have two significant figures. Calculating molar mass and density. So a gas-filled air balloon will either sink or float in the air depending on whether the density of the gas inside the balloon is greater or less than the density of the surrounding air. Gases do have different densities, and the gas density is measured in grams per liter and at a specific temperature. The density of a gas at STP and the molar volume at STP, 22.4 liters per mole, can be used to calculate the molar mass of the gas. And similarly, the molar mass of the gas and the molar volume at STP can be used to calculate the density of a gas at STP. So let's go through another sample problem where we have to calculate the molar mass of a gas at STP. The density of a gaseous compound containing carbon and oxygen is found to be 1.964 grams per liter at STP. What is the molar mass of the compound? So let's list our knowns. The molar mass of the compound is calculated from the known density of the compound and the molar volume at STP. So the density they give us, we know, is 1.964 grams per liter. And we know that 1 mole of the gas at STP is 22.4 liters. And the unknowns will be the molar mass that we want to know in grams per mole. So we'll first identify the conversion factor needed to convert density to molar mass, which we have, 22.4 liters per mole. And you will use the density and molar volume at STP to calculate the molar mass. Molar mass is equal to grams per mole, which is equal to grams per liter times 22.4 liters per mole. So that is the conversion factor, which compare and take into account the density and molar volume at STP. We'll multiply the given density by the conversion factor. So we're given the density 1.964 grams per 1 liter times 22.4 liters of sulfur dioxide divided by 1 mole. Those cancel out and we get 43.99 grams per mole. Does the result make sense? The ratio of the calculated mass, 44, to the volume, 22, is about 2, which is close to the known density, and the answer should have 4 significant figures. And the mole is at the center of all chemical calculations, and that's why we want to spend some time and make sure that we understand this really well. And to convert from one unit to another, we must use the mole as an intermediate step. So just keep that in mind, whether you're going from mass to representative particles to volume of a gas, we use the mole as that intermediate step. Thank you for listening, and we'll see you for the next section.